In the last lecture, we saw Europeans engage in an orgy of killing, all in the name of God and maybe geopolitics. By 1648, they had come to accept that Christendom was forever torn asunder, that Protestants and Catholics would continue to walk the planet, eyeing each other warily perhaps, but no longer hell-bent on exterminating each other. I would argue that that realization and accommodation were entirely rational, humanistic, and modern. Maybe it's better to just agree to disagree rather than to kill each other. I would argue further that rationality and humanism, here meaning a value for human life, were gaining ground in Europe as it entered the modern world, and that this was part of a major cultural shift, born of Renaissance humanism, that would revolutionize how humans saw the world and themselves. In the period after 1500, and accelerating after 1600, Europeans were beginning to apply reason and their powers of observation, less to questions about God, which seemed now too complex to resolve, hence the Peace of Westphalia, and more to the natural world in which they lived. The result was the rational and scientific revolutions. At first glance, the resultant scientific discoveries were neutral or harmless. What does it matter whether the Earth revolves around the Sun or vice versa? But in fact, the answers to these questions would change how humans thought not just about nature, but about God and about themselves. In short, they too would rend the great chain of being. Now, to understand why, we have to go back to the chain and the astronomical theory at its heart, the Ptolemaic universe. The Ptolemaic universe, you will recall, meant that in 1500, most people believed, along with Ptolemy, a 2nd century Egyptian astronomer, and based on Aristotle, a 4th century before the Common Era Greek philosopher, that the Earth was the unmoving center of the universe. Expanding outward in concentric rings or spheres were the moon, the sun, the planets, the stars, orbiting in perfect spheres or circles, because a sphere is the most perfect shape. The outermost sphere, or the primum mobile, was inhabited. The whole structure was traversed by angels. The closer one got to God's realm, the more perfect the sphere. So the moon was supposed to be less hilly and rugged than Earth, the planets and stars more perfect still. Now, Europeans embraced this model for 3 reasons. First, it matched their experience, their observations, and their common sense. After all, if you go outside and you look up, it does appear that the sun and the moon are circling us. Second, it was handed down from the ancients. As you may recall, medieval Europeans thought that the Greeks and the Romans were smarter than they were, that God had revealed knowledge to them. Third, it fit revelation. That is, this universe fit their biblical Christian worldview. In fact, you could argue that this system, or its acceptance by medieval Christians, was deduced from Scripture. That is, if the God of the Bible had created a universe, that's the assumption, this would be its logical arrangement, rather than being induced from observation. Now, the reason I say that this system was based more on deduction, assume a fact, then extrapolate from it, than induction, that is, gather facts and then generate a theory, was that in spite of what I said above about common sense, in fact, this universe did not really fit careful observation. If you observe the heavenly bodies over a period of time, as the ancient and medieval astronomers did, then you will know that sometimes the planets, in particular, don't progress in a stately fashion across the sky. Instead, they appear to stop, reverse course, then reverse again and continue on their way. Now, this made no sense. So Ptolemy invented epicycles, sort of loop-de-loops in the middle of orbits. The more medieval scholars looked heavenward, the more epicycles they needed if they didn't want to toss out their worldview. Now, this may seem silly today, but the alternative was to dismantle the universe. That's just what a Polish astronomer named Nicholas Copernicus did in 1543. In 1543, Copernicus publishes On the Revolutions of the Heavenly Bodies. In this book, he made the radical suggestion that perhaps the Earth is not the center of the universe. He posited a sun-centered system, a solar system in which the Earth was third. This would explain why some planets appear to be going forwards and others in reverse. We were all racing around the sun at different rates. Now, in fact, this theory too had been known to the ancient Greeks, but it was to early modern Europeans a shocking suggestion. How could common sense and the naked eye be wrong? How could 2,000 years of received opinion, Aristotle and Ptolemy, be wrong? How could the earth not be the center of the universe, not be the battleground of good and evil? Could the great chain of being be wrong? Why would humans be third? Is man just another creature? Was the Bible itself wrong? Almost no one in Europe wants to go there. There were other reasons for rejecting Copernicus, in fact. Scientists are not will-o'-the-wisps. They need to live with a new theory for a while before abandoning the old one. In fact, the math still didn't work out. It turned out that even Copernicus needed epicycles. Knowing nothing of gravity, he made the mistake of assuming that the planets orbit in perfect circles at the same rate of speed. Only later, when Johannes Kepler would propose elliptical orbits and Isaac Newton explain them with gravity, would Copernicus' system make sense. Fortunately for Copernicus, he didn't have to worry about these problems. He had the good sense to die the year after publication. The trouble he avoided was inherited by Galileo Galilei. Galileo was a professor at the University of Padua. He was a distinguished physicist. As a young professor, he took on an old Aristotelian theory by demonstrating that the rate of fall of a body is constant regardless of its weight. Aristotle thought that the heavier a body, the faster it would fall. Now, more importantly for our purposes, Galileo was the first major astronomer to turn the newly invented telescope to the heavens. Beginning in 1609, he discovered some alarming facts. Turns out, the surface of the moon is pitted and cratered and irregular. The surface of the sun is marked by spots. The planet Jupiter has moons of its own, implying that it was a model for a solar system. Venus has phases. There were many more stars than previously thought. In fact, Galileo discovered and mapped a great deal of the density, at least, of the Milky Way. None of this fit the great chain of being. The bodies closest to God should be more perfect than the earth. They shouldn't have phases or moons, craters. But this universe was messier, more complicated than that system imagined. Now, Galileo published his findings gradually in the 1610s and 20s. He was attacked by churchmen and other professors, and some of his work was banned. In 1614, Galileo responded with an open letter asserting the Bible's irrelevance for scientific knowledge, that it should be reinterpreted in the light of new discoveries. That was revolutionary. In 1616, Robert Cardinal Bellarmine of the Society of Jesus, the leading Catholic theologian of his day, told Galileo to shut up. He forbade Galileo from arguing that the earth moved. In 1632, Galileo tried at considerable risk to get around the ban by publishing his Dialogues on the Two Chief Systems of the World. It's written in the form of a dialogue between two characters, one supporting Ptolemy's theory, the other supporting Copernicus. The idea behind dialogue form is that Galileo doesn't have to come out and say which one is right, but the data very clearly point in the direction of Copernicus. Now, the church originally licensed the book, but within a year, Galileo was summoned before the Inquisition on grave suspicion of heresy. He was threatened with excommunication and torture, and in 1633, he was forced to abjure his book, which was publicly burnt. He was sentenced to life in prison, soon commuted to house arrest, and the sentence was to be read publicly in every university. Still, there is a legend that as Galileo was being led away, he muttered under his breath, "Eppur se muove." It still moves, referring to the earth. The church could silence Galileo, and they could ban his books. But as with Luther a century earlier, thanks to the printing press, thanks to rising literacy, thanks to better communications and transportation, his ideas circulated among university scholars, especially in Protestant countries. One of them was a German astronomer in the service of the Holy Roman Emperor, Rudolf II, named Johannes Kepler. As a Protestant, Kepler was not bound by the church's prohibitions. Kepler could make everything fit, in fact, by proposing that the planets didn't circle the sun, but revolved elliptically. In 1618 through 21, he published The Epitome of Copernican Astronomy, encapsulating his findings. In 1625, he published the Rudolphine Tables. So you don't have to be a great scientist to get something splendid like that named after you. You just have to pay for it, which provided precise mathematical tables which could be used to predict the orbits of the heavenly bodies. The math now fit. But this was even more destructive of the great chain. Ellipses aren't perfect the way circles and spheres are. Even more important than what was discovered here about the cosmos was how it was discovered. Copernicus, Galileo, and Kepler did not follow traditional scholastic methods in devising their new worldview. Medieval scholastics worked deductively. They assumed a first principle, say that the cosmos must conform to the Bible, and then they worked out from there. Copernicus, Galileo, and Kepler did not assume a first principle. They ignore or twist what didn't fit. Instead, they used inductive methods. They made no a priori assumptions. They collected facts and gathered observations of nature. Remember that Renaissance humanistic interest in nature. They used the telescope. In fact, Aristotle would have liked this. Out of these thousands of facts, a portrait of nature emerged, and from that, a theory, which was capable of being translated into mathematics, as Kepler did in his tables. The implication is that nature is rational, regular, predictable. The result was then modified as new observations were made. It is never an article of faith, whatever the church might say. These men were pioneering the scientific method, but they missed only one element. That element was to be supplied by an English government lawyer and official who proposed the next step, Sir Francis Bacon, later Lord Verulam. In a series of speculative philosophical works, The Advancement of Learning of 1605, The Novum Organon, a takeoff on Aristotle's original Organon in 1620, and The New Atlantis in later years, Bacon argued for A, no priori assumptions. If a man will begin with certainties, he said, he shall end in doubts, but if he will be content to begin with doubts, he shall end in certainties. Then, B, he argued for the primacy of empirical observation, leading to C, a theory, always provisional, expressed D in mathematics. This was, so far, the same method used by Copernicus and Galileo. Bacon added one last step, experimentation. You had to test the theory. The theory must always be falsifiable. This, by the way, is why creation science and intelligent design, however valid they might be in their own terms, can't be science, because you can't design an experiment to test them. Sir Francis had just articulated the scientific method, one of the most powerful tools for the achievement of truth in the arsenal of civilization. For the first time since perhaps the Greeks, it was no longer enough of an explanation to say, well, God willed it. Bacon argued that the method should be applied not just to study of the physical world, but to all human knowledge. And indeed, armed with the new method, 17th century Europeans produced a scientific revolution, an explosion of new knowledge. In France, Blaise Pascal invented the adding machine. René Descartes made advances in optics, and both most famously advanced mathematics. Pascal devised Pascal's theorem, and with Fermat, the theory of probability. Descartes systematized the study of curves and devised that alphabetical system for unknown variables, variable A, B, C, X, Y, Z, and the system of superscripts for powers. In the Netherlands, Anton van Leeuwenhoek perfected the microscope. Christian Huygens wrote a famous treatise on light. Dutch universities, not bound by Catholic taboos regarding the dissection of dead bodies, became famous for their medical training. In England, the physician William Harvey discovered the circulation of blood. The chemist Robert Bucholz discovered the law of pressure and volume, PV equals nRT, and wrote it up in a work whose title sums up the attitude of the entire age, The Skeptical Chemist. Edmund Halley, an astronomer based at my old Oxford College, New College, coordinated his observations of the heavens with mathematical formulae to predict the orbits of heavenly bodies and the return of comets, hence Halley's Comet. But the greatest of them all, the man who epitomized and revealed the potential of the scientific revolution, was, of course, Isaac Newton. Isaac Newton put it all together. As an undergraduate at Cambridge, he came to be influenced by the works of Galileo. It was here that he had perhaps his greatest achievement, the positing of the idea of gravity. If Galileo was correct that objects in motion stay in straight line motion unless restrained, why don't the planets fly off into space? Newton posited that there must be an attractive force between objects based on weight. That's gravity. That is, the same force that causes an apple to fall to Earth causes the planets to stay in their orbits. From this simple proposition came Newton's 3 laws of motion. Every body at rest or in movement remains so unless or until a force is applied to it. The change in motion is proportional to the force exerted. And every action produces an opposite reaction. To demonstrate how motion works and to explain and predict how the universe works, Newton developed the calculus simultaneously with Leibniz in Germany. In short, Newton used Bacon's method, observed phenomena, posited a theory, expressed it mathematically, but what was his experiment? I suppose the apple, except there's no evidence that the apple actually ever really happened or existed. The motions of the heavenly bodies themselves, that is, every time they ended up where Newton said they would be, in a way that confirms his theory. 3 centuries later, the space program verifies Isaac Newton every time something lands or rendezvous with a heavenly body, successfully. Newton published his findings in 1687 in the Mathematical Principles of Natural Philosophy, better known as the Principia. This book, and the work which lay behind it, caught the imaginations of European contemporaries because it was a complete world system to replace Ptolemy's. It explained how the universe worked to everyone's satisfaction. In the words of Alexander Pope, nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. The implication of the Principia was that God's universe ran according to natural laws. They were unchanging, they were rational, they were mathematical, they were discoverable using the scientific method. This is a revolution. It implied that humans could discover nature's secrets, God's secrets. These were no longer mysterious. If humans could discover nature's laws, they could discover nature's remedies. They could perhaps cure disease, increase the food supply, divert mighty bodies of water, build ever greater buildings, perhaps one day fly. Clearly, if humans could grasp these powers, then prayers and rituals were no longer your only recourse to change or avert your fate. God was, in fact, no longer necessary to explain the daily running of the universe. Perhaps he was not concerned at the fall of every sparrow. Perhaps God was more of a celestial watchmaker who designed the universe, wound it up, and set it going. This philosophy is known as Deism and would be very popular in the 18th century. Now, please understand that neither Newton nor his contemporaries were atheists. The age saw a continual flood of religious treatises, devotional works, and arguments. Newton himself wrote many religious works, including a commentary on the Book of Revelation. But human beings now had a much more powerful tool for understanding their surroundings in the scientific method. Many 17th century philosophers would try to apply it to human beings themselves. After all, if the free, unhindered human mind can discover the laws of nature via the scientific method, why could it not also discover the truth in religion, philosophy, social relations, etc.? Why couldn't accepted truths about human nature and divine nature, for that matter, be subjected to the cold, hard light of observation, reason, and experimentation? Thus, René Descartes attempted to apply induction and reason to human philosophy. He rejected not only a priori assumptions, but anything for which there was no rational proof. The only certainty was that thought implied existence. I think, therefore I am. Conservatives were appalled by this. Blaise Pascal, the great French mathematician, was deeply troubled by the inroads of science and mathematical reasoning into what he called the empty, cold spaces of the universe. In the Pensées, notes for a great religious work he never lived to write, he argued that man remained corruptible and imperfect. Therefore, his reason was unreliable. Man is merely a thinking reed. As Pascal wrote, the heart has reasons that reason knows not of. Pascal feared that the new science would lead to skepticism and atheism. Other conservatives, Bishop Bossuet in France, King James VI in Scotland, Robert Filmer in England, mostly retreated into reassertions of the great chain. According to King James, the state of monarchy is the supremest thing upon earth, for kings are God's lieutenants upon earth and sit upon God's throne. But this formula didn't seem to work anymore. Humanism, the Reformation, the wars of religion, and even the discovery of the New World raised disturbing questions as to where kings got their power, whether a bad king or one who worshiped God differently should be obeyed. During the wars of religion, both Catholic and Protestant theologians began to argue that a heretic king could be deposed. The Pope absolved Catholics of their allegiance to Elizabeth, and both sides used assassination as a weapon. So in the new scientific, secular, modern Europe, philosophers were increasingly called on to construct new justifications for the state. At least two sought to do so using the scientific method. Thomas Hobbes was arguably the most original thinker of the 17th century. His great work, written during a civil war in England when everyone was debating the origins of legitimate government, is Leviathan, published in 1651. He considered himself a scientist. Therefore, he rejected explanations for human behavior derived from the Bible, Greek philosophy, medieval scholasticism. Instead, like Galileo or a Newton surveying the heavens, he just observed people, and he came to the following conclusions. Man is a creature dominated by passions, appetites, and physical needs, far more animal than angel. He will satisfy those passions and appetites and those needs at the expense of his fellow men and women. Therefore, men in the state of nature, prior to their enacting government or society, are in a constant state of war. They're like atoms crashing into each other, constantly fighting for food, shelter, power. Note how the discovery of the New World forced European philosophers to think about human beings in this mythical state, what would happen to human beings if they weren't in civilization. According to Hobbes, the only alternative to the state of nature is for people to form a contract with some strong man to which they will give full, irrevocable power over their lives, their liberty, their property. A single absolute ruler. Now, Hobbes understands that we don't really want to do this. The ruler may turn into a tyrant. But he would argue that the state of nature would be far worse. To break the contract would lead to chaos. So science seems to lead to the same conclusion as religion. The best form of government is monarchy. But note that in this monarchy, God doesn't enter into the equation. Power originates with the people, not the supreme being. That is revolutionary. John Locke went one step further. If Hobbes is the most original thinker of the 17th century, Locke is probably the most influential, not only in Britain. In 18th century France, in 18th century America, arguably he's the great philosopher behind the Declaration of Independence. Perhaps one reason for Locke's success is that he worked for real practical politicians. He worked for the Whig politician Anthony Ashley Cooper, Earl of Shaftesbury, in the 1670s and 80s. He was his private secretary. And so Locke didn't spend a whole lot of time in the ivory tower. In fact, in the 1680s, he actually has to flee England because of his political opinions. So he knew real experience. He published his two greatest works in 1690, the Essay Concerning Human Understanding and the two treatises of government. Now, to understand Locke's political philosophy, you have to understand his philosophy of knowledge and being, his epistemology. So we'll start with the essay. Like Hobbes, Locke claimed to be a scientist, an observer of men. But unlike Hobbes or traditional Christian theology, he did not believe in the natural depravity or rapaciousness of men. Rather, Locke believed that human beings are born neither good nor bad, but more or less as blank slates, tabula rasa. That is, he believed that environment was more important than any pre-programmed human nature, today we might say genetics, in shaping human character. Now note what that implies about the great chain of being. Maybe you weren't programmed to be a peasant. Maybe with the right training, you'd make a fine king. Now, Locke would probably have rejected that, but it's implied in his philosophy. He believed further that human beings are naturally rational, that reason, if left alone, would lead to decent moral behavior, even Christianity. In the treatises of government, Locke rejects a biblical basis for government, as well as the idea that kings are a species of father. He agrees with Hobbes that authority for government comes from the people in the form of a contract. But he argues that human beings get out of the state of nature by actually making two contracts. The first is with each other, to form civil society. The second is with a ruler to form government. Now this business of two contracts explains Locke's theory on resistance. Locke believes that human beings form government to protect their lives, their liberty, and their property. If any government fails to do that, the people retain a right to rescind the contract with their rulers and, in effect, depose them. Chaos would not ensue because they have not dissolved the contract of civil society. This bold idea contradicts the great chain of being. You can depose your ruler. It would be used to justify revolutions in Britain in 1688, in America in 1776, in France in 1789, in South America in the 19th century. It will infuse our Declaration of Independence. In 1701, Locke published his important letter on toleration, which provides a philosophical basis for arguing that toleration is the most rational position for Christians to take with each other. Thus, John Locke, Isaac Newton, and friends have pursued Renaissance humanism with its emphasis on human concerns and rationality to its logical conclusion. Humans are rational and by and large good. They are capable of understanding the universe, of changing it to suit themselves without God's help. They are capable of establishing societies and establishing governments, and even dissolving the latter and starting over again without God's help. Now, this does not mean that Newton, Locke, et al. Were atheists. They were just more self-reliant, more confident, more tolerant of different points of view than their medieval counterparts. Their lifetimes would see the beginnings of a new way of thinking as human beings came to believe that they could master their environment. The late 17th century would see, and I will end with these two developments. First, the first consistently successful surgical operation, cutting for stone. Samuel Pepys underwent this painful procedure in 1658, and he always thanked God on the anniversary that he had survived it. But the point is that he and lots of other people survived it. The other thing about the late 17th century is you get the first insurance companies. Well, what do these two seemingly disparate developments have in common? They both mark a refusal to accept fate, a refusal to accept God's will. I'm going to have this surgery. I'm going to change my fate. I'm going to be cured. In the case of insurance, what does insurance actually say? It says, terrible things can happen to you. What insurance companies still to this day call acts of God. And what we will do is, we will rebuild your house. We will rebuild your life. We will not let the act of God stop you. This confidence in human abilities, this sense of entitlement to a good life, liberty, property, or as Jefferson would have put it later, the pursuit of happiness. This refusal to abide by the decrees of nature, of kings, of God. This is all profoundly modern. But as we have seen, not everyone shared these views. The 17th century would see the forces of conservatism, churches, monarchs, mount a dramatic rearguard action. The result would become the crisis of the 17th century. In the next lecture, we turn to that crisis and two solutions which will set the tone for politics in Europe for hundreds of years: French absolutism, and in subsequent lectures, English constitutionalism.